All right, my second airtime. I want to, so this will be, yeah, about another tool that we have at ProbeLab have built. So it's called Nebula, and I would describe it as a network agnostic DHT crawler. And so network agnostic means it doesn't, it's not only crawling, for example, the IPFS DHT, which we call Amino, like the public Amino DHT, but it can also crawl networks like the Ethereum, especially the consensus layer. As I've learned today, the execution layer is like, it seems to be a subset of the consensus layer, but yeah. Filecoin is another one, Polkadot with Kusama, Rococo, and West End, and since yesterday, also Celestia mainnet is also another network that Nebula can crawl and supports. You can find it on the right-hand side, so this is the repository. And yeah, basically any other libp2p-based DHT is also supported by Nebula. And we at ProbeLab use it extensively for metrics and so on. And I want to demo it today, so pray for the demo demons. Let's see. So let me remove that first. So I have Nebula installed here, and when you run Nebula help, there are plenty of command line options. Is it big enough? Should I? Hang on. Okay, now it's, yeah. Just let me know if I should increase the font size here. So there are two, or no, yeah. So the two main top-level commands are crawl and monitor, and I will only go into crawl today. Well, we can briefly run Nebula networks, because this will just give you a list of all the supported networks. So it's IPFS, Amino is just an alias for IPFS, and then all the other networks that you've just seen on that slide. And if you want to dig deeper, for example, for IPFS, you will receive the protocol string that Nebula would look for, and all the bootstrap peers that Nebula would start the crawl from. And I haven't explained what crawling means, so it means we connect to the bootstrap peers, which are, in this case, hard-coded, but you can also give it a list of bootstrap nodes on the command line or through environment variables. It will connect to these bootstrap peers, construct certain keys that fall into each of these buckets that these peers maintain, as according to the Academia specification, and then ask these peers to ever closer peers to these specific keys, which then yield new peers to look for in the next iteration. So it's like a recursive algorithm until it exhausts not the key space, but all the available peers in the network. And well, this can take a variable amount of time. And so let's look at the crawl help page here. So this says we have like a network flag, and if we wanted to crawl, for example, the Celestia network, which is supported since yesterday. So let's see, Celestia. Something that you might have noticed on the previous help page, I can give it a dry run flag here, which means we won't save anything, we won't store anything in a database or so on. We will just print the crawl to the to the console. So let me clear the console and just run it. Fingers crossed. So here you can see that there at this time 26 peers in flight. There's one in flight here. We are waiting for that one to finish. And yes, the dry run is doing networking, but just not in no persistence. Yeah, correct. Of course, it's blocking. It should only take like 5 seconds to time out, and it doesn't. Oh, I tried this so many times. Man. But you can already see a few things here. So we found 138 peers in the network. Ah, here we go. So it finished. So it timed out after 46 seconds. Yeah, thank you. It worked. And in this case, it just prints some summary statistics to the console here. And what we can see, there are some dial errors. This means we couldn't connect to a few peers in the network because of various reasons. In some cases, we didn't have a public IP that we could connect to. Some peers just refused the connection. Some other peers reset the connection. We weren't able to negotiate the security protocol. And yeah, for 25 peers, we ran into a timeout. And we found 74 peers in the network, which advertised the Celestia-Celestia agent version. Would be great to have a version in that string. Sorry? Yeah, sure. Yeah, I will put a thumbs up on that. And yeah, then this part here at the bottom actually shows you the protocols that we found in the network. For example, 74 out of these 74 dialable peers actually support the IPFS ID 1.0 protocol. And then there are some Celestia-specific ones like Celestia/fraud, SRHREX, Threx, sorry, and some other Celestia-specific protocols. And we can do the same thing not only for Celestia, as I said. Let's do it for the IPFS DHT. Oh, sorry. Yeah, go ahead, Chad.
Yeah, I mean, when it cleared it up, but I was just looking at the count for the dial errors, and I noticed that the amount is actually higher than the amount of peers that we dial.
For the protocols, you mean?
Yeah, so the dial errors, I saw like, I don't know if you'll be able to bring it back up.
I don't, but we can just do it again. If it won't take, so because it's the first time that it took 46 seconds actually. Yeah, here we go.
So for the dial errors, there are the counts. What are on the actual dial errors that is, I should say? So it's the count 11, 14, 15, and 25.
So actually, this should add up to 65. I'm not sure. Does it? So 1, 5. Yeah.
Okay, so each one of those counts is the actual is like an individual dial error.
Yes, exactly. Yeah, yeah.
So I was wondering if you could be more, because for me, it would seem more intuitive to actually say which pairs those were by whether by
Right.
or whatever.
Right. Well, this is only like for diagnostics after you, basically just for demo purposes, because usually you would dump it to a file or to write it to a database. And yeah, I think it could be made more intuitive, definitely, in this case. But yeah, these are like individual errors that we encountered, and yeah, should add up to this number here at the bottom. Yeah, cool. Then just brief demo of IPFS, and we can actually limit the crawl because the IPFS DHT has around 20-something thousand, and if we just limited it to 1,000 peers to crawl, we can do that. Let me make it a bit smaller. So we have processed 400, 500. You can see it here at the bottom right. And as you can see, so there's this. Yay, done. You can see it here. There's like a large number of peers queued. So these are the ones that we've identified in the network. But as I've configured it on the command line, we stopped after 1,000, which has happened here. So processed 1,000. There's still 1,000, almost 1,000 in flight. And yeah, but we stopped now after 1,000. And here again, we see a couple of errors, and then all these different agent versions. We see Kubo 0.19, 18-def, and yeah, all this kinds of stuff. And for research, I think it's quite interesting to see if we, instead of did a dry run, we can output it as a JSON. So if I pass it the JSON out command line flag and said, okay, please dump it into this specific directory. And let's use Celestia again, just because. Celestia. And yeah, remove that one. Yeah. Okay, just once again. Here we go. And now we find 4 different files in this directory. And for example, this first bit here, let me just pipe this into JQ. Here we can see some general statistics about the crawl, so that it succeeded, when it started, when it finished. These 2 fields are actually only relevant if we stored stuff into a database, into Postgres. And Postgres is the only database that's supported. Then in these crawl properties, also let's pipe it to JQ, we can see all this summary information that we've also seen on the command line. And probably also quite interesting is this visits. So every time we try to contact a peer, I consider this a visit. So let's just, no, let's not do cat, but just only take the first row. So there actually, like we can see if we did this, there are 139 rows in this JSON file. So it's a new line delimited JSON file. And this corresponds to every node every peer that we found in the network. And at the top here, we only look at the first one. So we see the peer ID, the multi-addresses. It would support if we were able to connect to it, to this one, but we had no public IP. So maybe let's take the first 2, perhaps. Yeah, here we go. So the second one actually has more information. So we have the multi-addresses of that peer. the supported protocols of that specific peer, the agent version that it advertised, how long it took to connect to this peer, how long it took to drain the buckets, and just some timestamps and potential errors. And also properties, which are relevant if you want to crawl, for example, the Ethereum DHT. Then properties would include information like fork digest and attestation numbers. And this is basically just a free-form key-value map that you can fill with anything depending on which network you want to crawl and so on. And then there's this last file here. And this is like the last bit, and then I will. Cool. This file's empty because this would contain neighbor information. And to gain to collect neighbor information, we would need to pass this the neighbors flag, because this is quite a lot of information. So I disabled it by default. So you specifically need to enable this, and this will, well, let's just do this, and then I will show you what it will contain. Okay, come on. Well, now you've seen that it actually works. So let's see. Yeah, so I disabled this because it's quite a lot of information. So it's, especially for the IPFS DHT, when I enable this -- neighbor flag, this file will be like 200 or 300 megs in size. And now this one is, okay, 300 kilobytes compared to a few dozen bytes, basically. So when we take a look at this file here, and let's again take just the first line, pipe it to JQ, we can see that this particular peer in the network had all of these other peers in its routing table. And this allows us to reconstruct the complete topology of the entire network. And yeah, this allowed us to do things like the routing table health study that Guillaume, another colleague of mine, did, I think, beginning of the year or end of last year, as well as when we had this major incident in the IPFS DHT earlier this year to identify that the impact is only visible in the higher buckets. So we could use this crawl data to see how the routing tables actually perform in the IPFS DHT. And yeah, I think that's it. Well, just a brief information about this monitor thing. So when you actually use instead of using JSON as the output data as the persistence layer, you can also use Postgres databases Postgres database, and then when you run Nebula monitor, Nebula will take all these peers that it has discovered as being online and active, and try to reconnect to them with an exponential backoff, like the first time after 1 minute, and then if it has replied successfully, then after another 2 minutes, 4 minutes, and so on. And this allows us to monitor the uptime of all the peers in the network and calculate things like churn. When churn, for example, is important for DHT network-wide parameters like the replication factor or routing table refresh frequency, for example. And yeah, so this is all done by ProbeLab. So we are running Nebula for the IPFS DHT, for the Polkadot.DHT as well, Polkadot network as well. Right now, not for Celestia yet. So maybe let's chat afterwards. And in general, so this is our mission. So yeah, we at ProbeLab, we do network measurements and protocol optimizations, especially because things might not work. Things might work, but not as you expect them to work. So as you can see on the right-hand side, yeah, we've done a lot of things over the last few, within this year especially. We realized latency gains, as I mentioned, this last big incident at the beginning of this year. Realized huge cost savings by analyzing how Hydra boosters, for example, impacted the network, and yeah, a few other studies as well. And so one call out perhaps to the community. So we have a roadmap that we put together. We specifically want to look into the performance of IPNS and gossip sub, as well as LP2P bandwidth requirements, especially when two peers connect to each other, what is the overhead, and so on. And we would like to have feedback and perhaps also some funders here. I don't know, Janis, if you want to chime in or so. Yeah.
Yeah, so we're still putting together the roadmap. These are the suggested items that we have collected out of our own insights, out of discussions with other teams within and outside protocol labs and the wider kind of lip2p space. But of course, yeah, this is not final yet. You can influence the roadmap and what the team is going to be working on. Yeah, the sooner the better, obviously. Yeah.
One next slide. Yeah.
Yeah, so we have several sponsorship tiers that someone can get involved in. I can send more details in the lip2p channel in Telegram that we have set up. But basically, you know, there are several benefits that come according to the sponsorship tier. The very basic, you know, basically influence the stack ranking of the roadmap items that we have just mentioned, or new items can be added if, you know, with higher sponsorship tiers, or basically, you know, we can work on a tailor-made project for the team or project that you're building on. All of these obviously subject to effort needed to do all that. Yeah, so basically we want to help cultivate a data-driven protocol design and optimization culture in Web3, because we think that that's the only way to start gaining adoption and, you know, ultimately get application developers to build on top of these great technologies that we're building, not only in lip2p and IPFS, but also, of course, the wider Web3 space. So it doesn't, all of what we're doing does not apply only to IPFS. That's why, you know, it's lip2p day here. It applies to the entire, to all the dependents of lip2p, and by doing things improving things at the network layer, you know, you collectively lift up all the applications that build on top of them. That's why, as said previously, you know, the network layer has been kind of underestimated, overlooked in many cases in this space, and we want to turn this around.
Yeah. Just a quick one. With the neighbors JSON with Nebula tool, I'm wondering if there is a visualizer. You said you can basically reconstruct the DHT topology, and I'm wondering, is there an existing visualizer for that, or is that something that somebody could contribute to Nebula? Because I see that as being pretty valuable as like a monitoring tool, and you could visualize the connectivity status with, you know, the monitor in that visualizer to show it like flickering if it's not always on, etc.
So actually our logo, the ProBlab logo, this is the visualization of the IPFS DHT.
Sweet.
And we generated it from a tool called GraphXT, I think. That's how it's called. But this was a one-off thing, and it would be great to have something that could actually just take the format that this tool spits out and generate a visualization here. Many of these graph tools use something that's called an adjacency list. And in the Nebula repository, I have like a one-liner, which is a JQ one-liner, which takes this neighbors JSON and turns it into an adjacency list, which can then be imported into many of the graph visualization. I'm not sure visualization, but at least analysis tools. Yeah. But it would be great if someone contributed that.
Yeah. Excellent. Thanks. Oh, Chad has one.
Yeah, earlier on you're mentioning crawling the Ethereum DHT and then subsequently getting the Fort digest from the properties. I mean, so just for context, I was trying to build an Ethereum crawler myself, but I understand that for pair discovery, Ethereum uses this v5.
Correct.
So then how does this then plug into that to then pull the Fort digest to get the ENR records, I guess? Is that possible here, essentially?
Right. I mean, we can have like a quick last one. So let's take the Ethereum consensus, I think it is. Hang on, but let's limit it to, I don't know, 500 or so. So, yeah, so you can take an ENR record, and there's like a clear mapping from a node ID in an ENR record to a peer ID. So I'm reusing a lot of these very flexible lip2p abstractions like peer IDs and multi-addresses. And in this case, I'm just so the core of Nebula is quite generic and agnostic to the DHT implementation. There are a few interfaces that just need to be implemented, and then the core of Nebula can actually be used with a lot of different DHTs. And right now, I've only done this exercise for like the the lib-P2P implementation of DHT implementation and the disk v5 implementation. And the next logical step for me would be to also support disk v4. But yeah, as I said, it could be anything in this case. And yeah, the constraint would be the node ID would need to be transformable to a peer ID. And when you mentioned this this properties thing, let's take a look at this just quick. Oops. Ah, come on. Sorry. So here, in this case, this properties map is filled with some information extracted from the Ethereum node record. In this case, the fork digest, next fork epoch, sequence numbers in the signature. Could be much more. And credit goes to Mikkel, actually, for the parsing of all of that. And yeah, so it's or hang on, what was your question, actually? Now I'm showing just how it works.
No, I didn't know that this existed because I was trying to see essentially how many Ethereum nodes were running this v5 and lib-P2P at the time. But
right. Yeah. I tried to find a common abstraction of for both networks, and yeah, this was quite an undertaking because Nebula at first assumed quite a few things to be lib-P2P specific, and now, yeah, just a few weeks ago, I did the exercise of making it more generic. On the actual DHT implementation. Yeah.
Amazing tool. Just for clarification, like the Ethereum consensus layer uses this Discovery 5, but Discovery 5 is just an implementation that many other project uses. That's why there are so many entries on the DHT more than the actual nodes that participate on the Ethereum consensus. And there are also, despite their consensus nodes, let's say, there are also testnets that use Discovery 5. So it's a tricky thing. Like, yeah, it's like a shared ground, like the lib-P2P DHT uses for several projects, rather than purely Ethereum consensus oriented.
Thank you.